In this video, I will explain the main pieces of notation that we commonly use to talk about sets. What is a set? We're going to think of a set simply as a collection of things. For us, most of the time it will be sets of numbers, but it could be anything. And we call those things the elements of the set. I put an asterisk here because if you ask a logician, they will tell you this definition is not good enough. And they would be right. For the purpose of logic and foundations, this definition is problematic, but for our purpose, it's good enough, so we're going to keep it simple and go with it. Here are two examples. I'm describing two sets here, and I've given a name to both sets. The first set is called A, the second set is called B. And when I describe the set, I use curly braces to indicate where the description begins and ends. And I'm describing them differently. The first set is the set of all even integers, so this set has infinitely many elements. For the second set, I've provided a complete list of the elements. So B is a set that has three elements, the number 4, the number 5, and the number 6. Next, sum notation. These two symbols are used to indicate that something is or isn't an element of a set. I'm going to use these three sets, B, C, and D, to construct examples. So using that, for example, I can say that the number 4 is an element of B, but the number 2 is not an element of B, because it's not there. This symbol is different. This represents the relation between two sets. It means that a set is a subset of another set. For example, here I can say that D is a subset of B, because D is contained in B. All the elements of D are also elements of B. However, this symbol comes with a warning. Unfortunately, the notation for subset is not universal. Some books like to use the symbol I introduced to indicate that something is a subset and may be equal. And then they use this symbol, the same one without the extra horizontal line, to indicate that it may not be equal. But other books use the second symbol to indicate something is a subset and may be equal, and then introduce yet a new symbol, this one, to indicate it may not be equal. And of course this is confusing because the same symbol may mean two different things. My preferred solution is to always use these two symbols only, and then there is no ambiguity. But what really matters is that when you read a math book or you do math with someone, you agree on which notation you are going to use. Back to more notation. These two symbols are used to describe operations with sets, how to construct a new set from all sets. This symbol means a union of two sets. So a bigger set we construct by putting together all the elements in each one of them. For example, here, I could construct the set C union D by putting together all the elements of C and D. That would be the set with 2, 4, and 5. And this symbol is the intersection of sets, a new set that contains only the things that are in both sets. Using the same example, C intersection D could be a set with only one element, the only thing they have in common, which is the number 4. And finally, this symbol is used to denote a specific set, the empty set. That is a set that has no elements. So another way to describe it could be a set where the list of elements is, well, empty. To conclude, I want to introduce 4 important sets of numbers that we use often. Everybody uses the same name for these 4 sets of numbers, and the same notation is these uppercase letters with an extra bar. N stands for the natural or counting numbers, the ones you've been using since kindergarten. Well, this comes with a caveat. I started them at 0. Some books begin them at 0, some books begin them at 1. Don't get into an argument about whether we should include 0 or not. That's a waste of time. There are good reasons to include it or not to include it. What matters is that when you do math, when you read a book, you just make sure you know which convention you are using. Next, Z represents the integers. Those are the natural numbers and also their negative counterparts. Next, Q represents the rational numbers. Those are the fractions, the quotients of integers. And finally, R represents the real numbers. For our purposes, I'm simply going to say that the real number is any number with a decimal expansion. There is a better, more formal and rigorous way to define the reals, but that is surprisingly deep and complicated. That's normally the topic of an analysis course. To conclude, notice that these subsets are bigger and bigger. Each one is a subset of the next.